Okay, what I want to look at here is time constants for capacitors. Should already have seen the charging and discharging graphs by now. This is voltage against time. This is the one you really need to remember. It will help you. There's going to be 4 graphs we need to know about for capacitors and 4 for inductors. This is the only one you need to remember. You will see a demo, hopefully, where the voltage across the capacitor slowly increases, which means that if we've got a circuit like this, which we've seen before, this time we'll make it a lamp and a capacitor. The lamp, when we open the switch and then close it, the capacitor is going to charge. At first the capacitor's got, let's say that's 12 volts, at first the capacitor's got 0 volts, and the lamp is nice and bright. As the capacitor charges up, less current flows, and it gets to a point where no current flows. The lamp will slowly dim. So we've got 2 curves, the discharge curves. Not the discharge, but the current time graph. This is charging. And the other 2 graphs we've got are discharging. That's when we open the switch. And when we open the switch, it's all charged up to 12 volts, but when we open the switch, what's going to happen is, especially if we can open it, so this is no longer connected, right? That's no longer connected. If we then have it connected up so that it can discharge, then we'll get a flow of current back through the lamp as it discharges. So capacitors are great storage devices. You charge them and then they can release their charge very quickly. So the way to think about capacitors is as storage devices for charge. All right, that's what they are. And we charge them, up they go. The voltage does that, the current does that. Then we discharge them, the voltage drops, and the current drops. The current starts off quite high because when you first open up the circuit here and break that and connect this one, the charge is high, the voltage is high, but as it goes through the lamp and discharges, the voltage gets less, so the current drops. Looking at actual numbers, if the EMF is 12 volts, then this little guy will charge up to 12 volts. It will start as if there's no capacitor, so the current will be 12 volts divided by the resistance of that lamp, and it will drop down to 0. The voltage will start at the 12 volts when it discharges, and the current will start as if, again, the voltage supply is perfect, and therefore 12 over R, but it will slowly drop off. So we can determine the numbers on those graphs. So far, so good. But what we actually need to also do, and I don't know if I'll show you, I may show you in another graph, what we have is equations for these ones. So if you look at the next video on these guys, you'll see the equations. You don't need to know them though for level 3, but it helps see where this whole 37% number comes from. And what am I talking about here? I'm talking about something that is called time constant. Now, time constant, the formula for it is RC. Resistance in ohms times capacitance in farads will give you a number in seconds, and it's called the time constant. And for graphs that look like this, like that, the 37% tells you that after one time constant, so if that's one time constant, remembering like for our circuit, this could be the current starting up at V over R. This is a current time charging graph. If I want to know what the current is after one time constant, which is equal to RC, then after one time constant, the 37% is what the current will be. Graphs that look like this, one time constant is 37%. Right? 2 time constants over here, right, is 0.37 squared. Right, so if we do 0.37 squared, we get 0.1369. So if I want to know after 2 time constants, then That's pretty much 0.14 or 14%. 3 time constants, so that was 2 time constants. 3 time constants would be 0.37 cubed. And you can work out the current as time goes by in the circuit. This is a real simple way of looking at it. Just going, these graphs, 37%. You want to know, after 1 time constant, it's down to 37%. After 2 time constants, it's down to 14%. After 3 time constants, it'll be down to 0.37 cubed. Now, the other number that's really important is 1 minus 0.37, which is 0.63. This is useful for graphs like this. And what it tells you, and this could be the charging graph, we've got voltage over time. It's charging up to the 12 volts. This is like an asymptote, getting closer and closer. You want to know after 1 time constant, where is things at? Time constant being RC. After 1 time constant, it's going to be at 1 minus 0.37 or 0.63 of its final value. So we can go after 1 time constant, it'll be at 0.63. What about 2 time constants? So that was 1 time constant. 2 time constants is equal to 1 minus 0.37 squared. All right, now we said 0.37 squared is equal to 14%, so that equals 0.86. So after 2 time constants, then that would be 0.86 of its final value. So this is 0.63 times 12, and this one is 0.86. 3 time constants, we equal 1 minus 0.37 cubed, which will equal whatever it is, 90% or something, 90-something percent. Usually on your graphs, do 3 time constants and put the numbers in. That's what you need to get the credit for these type of graphs. If you want to know the equations for the curves and where this wonderful 0.37 comes from, have a look at my next video on time constants and equations for the graphs.